Here in Section 2, our objective is to explain the role of the General Hazardous Materials Behavior Model in predicting the behavior of containers. In order for the first responder to protect themselves and others, they must understand how a hazardous material and its containers are likely to behave in any given situation. The behavior typically follows a general pattern. The General Hazardous Material Behavior Model, often referred to as the General Emergency Behavior Model, GEBMO, describes this general pattern. This model is based on Ludwig Benner Jr.'s definition of hazardous material as things that can escape from their containers and hurt or harm the things that they touch. The model assumes that hazardous materials incidents have the following common elements: material or materials presenting hazards to people in the environment or property, container or containers that have failed or have the potential to fail, exposure or potential exposure to people, the environment, and or the property. Given these three elements, material, containers, and exposures, a common sequence generally occurs. Stress can cause the container to undergo physical, thermal, or other types of damage that reduces its ability to function and leads to breach or failure. Breach is when the container becomes open to the environment. This opening depends on its construction material, type of stress that it undergoes, and pressure inside the container at the time that it fails. A breach or failure of the container may be partial, such as with a puncture, or total as a disintegration. The release is when a container breaches or fails, and contents stored energy and pieces of container may be expelled into the environment. A release always involves the hazardous material product and may, depending on the product, container, and incident condition, involve the release of energy and container parts. With dispersion and engulf, this occurs as the hazardous material inside the container and any stored energy releases and moves away from the container. Patterns of dispersion are influenced by chemistry, physics, environmental factors, and the chemical and physical characteristics of the product. Exposure and contact is anything such as persons, the environment, or property that is in the area of the release and is exposed to the hazardous material. Harm is depending on the container, hazardous material, and energy involved. Exposures may result in harm or damage. Stress in the container is caused by thermal energy, chemical energy, and mechanical energy. With thermal energy is excessive heat or cold and could cause intolerable expansion, contraction, weakening, or consumption of the container and its parts. Thermal stress may increase internal pressure and reduce container shell integrity, resulting in sudden failure. Thermal stress may result from the heating or cooling of the container. A container undergoing excessive heat may be extremely close to flames, undergoing the operation of a relief device, making noises of expansion or contraction, and or subject to changing environmental conditions such as increased temperature. A container succumbing to cold may exhibit excessive frosting, visible cold vapors, changes in steel structure, smooth to grainy, and pools of cold liquid. Chemical energy can be uncontrolled reactions or interactions of the container and its contents. Chemical reactions or interactions could result in the following: a sudden or long-term deterioration of the container, excessive heat and or pressure causing deterioration of the container, corrosive or other incompatible interactions between the hazard material and the container material, visible corrosion or other degradation of the container surfaces, including bulging, cracking, and or popping noises, and the interior of the container may experience chemical stress with no visible indication from the exterior. Mechanical energy is the physical application of energy that could result in container or attachment damage. Mechanical stress may change the shape of the container by crushing, reduce the thickness of the container surface by abrading or scoring, cracking or producing gouges, and unfastening or disengaging valves and piping, or penetrate the container wall. Common causes of mechanical stress include collision, impact, or internal overpressure. Clues of mechanical stress include physical damage, the mechanism of injury, such as a force placed on the container, and the operation of relief devices. According to U.S. Department of Transportation records from 2006 and 2014, nearly 41% of all reported hazmat incidents were attributed to container failure. Responders may encounter one or all three of the stressors at any hazmat incident. For instance, heat, such as thermal stress, can initiate or speed a chemical reaction while weakening a container and increase its internal pressure, such as mechanical blow can initiate a violent chemical reaction in an unstable chemical while simultaneously damaging the container. When evaluating container stress, you need to consider the following: the type of container, the product in the container, the type and amount of stress, and potential duration of stress. Container stress may involve a single factor or several stressors acting on a container simultaneously. Preventing container failure may require reducing or eliminating the factors placing stress on the container. Those factors may be readily visible, such as a collision or a fire impinging on the container surface, or there may not be directly observable and must be predicted based on conditions or other indirect indicators. And if the container has already failed, think about other containers that may be exposed and evaluate the impact of product contact with the other containers. The material state of matter will affect the stress experienced by containers. For example, containers holding gases are inherently subject to stress. Heating or cooling may increase or reduce these stress. These containers may fail catastrophically and or levy if they are damaged or subjected to additional stress, such as heat from a fire or even hot daytime temperatures. Liquid containers, especially those holding liquids with high vapor pressure, may also fail when subjected to fires. Liquid containers may also transport materials that plumerize. This is a stress created by an uncontrolled plumerization, which is a chemical stress caused due to container failure. This failure may be explosive. Most solid containers will be damaged via mechanical stressors rather than the physical properties of the materials contained in them. Exceptions would include reactive materials from hazard classes such as explosives, oxidizers, peroxides, and water-reactive materials. Warning: use extreme caution when working with containers that have been involved in an accident. Breach is when a container is stressed beyond its limits of recovery. It opens and breaches and releases its contents. Different container types breach in different ways, based on the variety of factors including internal pressure. The type and extent of breach depends upon the type of container and the stress applied. First responders should try to predict the type of damage that may result from the stress that is being or has been applied. The nature of the breach is a major factor in planning offensive product control operations. Types of breaches include disintegration, which occurs in containers that are made of brittle material or that may have been more brittle by some form of stress. The container suffers a general loss of integrity, and examples of disintegration may include a glass bottle shattering or an exploding grenade. Runaway cracking is when the container breaks into two or more relatively large pieces by fragmentation or large tears, such as when a crack develops in a container and continues to grow rapidly. Runaway cracking often occurs in closed containers such as drums, tank cars, or cylinders. Runaway linear cracking is commonly associated with levees. Attachments may fail, open, or break off when subjected to stress, leading to a total failure of a container. When evaluating an attachment such as pressure relief device, discharge valve, or other related equipment that failed, first responders should consider the entire system and the effect of failure at any given point. The puncture occurs when a foreign object penetrates through a container, such as a forklift puncturing drums and couplers puncturing a rail tank car. Splits or tears is when containers may also breach through a split, such as a welded seam on a tank or when a drum fails. Mechanical or thermal stresses may cause splits or tears, such as when a seam or on a bag of fertilizer rips. Release is when a container fails, its contents, energy, and the container itself, whole or in pieces, may release. If a cylinder or pressurized chlorine gas suffers an attachment failure at the valve due to mechanical stress, the product is a toxic corrosive oxidizer releases along with a substantial amount of energy because of the stored pressure, which rapidly accelerates the valve and or the cylinder in the opposite direction from the release. Depending on the situation, this release can occur quickly or over an extended period of time. Generally, large amounts of stored chemical or mechanical energy may result in a more rapid release, presenting a greater risk to first responders. Releases are classified according to how fast they occur. Detonation is an instantaneous and explosive release of stored chemical energy of a hazardous material. The duration of a detonation can be measured in hundredths or thousandths of a second. An explosion is an example of a detonation. This release could result in fragmentation, disintegration, shattering of the container, extreme overpressure, and considerable heat release. Violent rupture is an immediate release of chemical or mechanical energy caused by runaway cracks. Violent ruptures occur within a time frame of 1 second or less. These releases result in ballistic behavior of the container and its contents and or localized projection of the container pieces or parts and hazardous materials. A levee is an example of a violent rupture. Rapid relief is a fast release of a pressurized hazardous material through properly operating safety devices. This action may occur in a period of several seconds to several minutes. Damaged valves, damaged piping, damaged attachments, or holes in the container can result in rapid relief. Spill or leak is a slow release of hazardous materials under atmospheric or head pressure through holes, rips, tears, or unusual openings and attachments. Spills and leaks can occur in a period lasting from several minutes to several days. Dispersion and engulfment is sometimes referred to as engulfment. Dispersion of a hazardous material, energy, and container components depend on the type of release, which includes a solid, liquid, or gas vapor, mechanical, thermal, or chemical energy and ionizing radiation, or product characteristics and environmental conditions such as weather and terrain, which could include physical and chemical properties, prevailing weather conditions, local topography, duration of the release, and control efforts of responders. The shape and size of dispersing hazard material also depends on how the material emerges from its container, whether as an instantaneous puff, a continuous plume, or a sporadic fluctuation. The outline of the dispersion hazard material, sometimes called its dispersion pattern, can be described in a number of ways. Common dispersion patterns include hemispheric, which is a semicircle or dome-shaped pattern of airborne hazard materials that is still partially in contact with the ground or water. A hemispheric release generally results from a rapid release of energy such as detonation or violent rupture. The following elements are common to hemispheric releases. One is energy, and it generally travels outward in all directions from the point of release. The second is dispersion of energy. It is affected by the terrain and cloud cover. Solid cover can reflect the detonation shock wave, increasing the explosion impact. And finally, energy release. It may propel the hazard material and container parts. However, this dispersion may not be hemispherical. Large container parts generally do not always travel in line with the long axis of the container. The cloud is a ball-shaped pattern of the airborne hazard material that collectively rises above the ground or water. Gases, vapors, and finely divided solids that release quickly can disperse in cloud form under minimal wind conditions. Terrain and or wind effects can transform a cloud into a plume. The plume is a irregular shaped pattern of an airborne hazard materials where wind and or topography will influence the downrange course from the point of release. Dispersion of a plume, generally composed of gas and vapors, is affected by vapor density and terrain, particularly in vapor density is greater than 1, as well as wind speed and directions. Other plume dispersion elements include the following. The plume release is when all of the material is released at one time. The concentration of gas or vapor in the cloud or plume and decreases over time. The ongoing release is when the concentration increases over time until the leak stops or all of the product releases, then it decreases. The cone is a triangular shaped pattern of a hazard material with a point source at the breech and a wide base downrange. An energy release may be directed and may project a solid, liquid, or gaseous material in a three-dimensional cone-shaped dispersion. Examples of cone-shaped dispersion include container failures in a levee or a pressurized liquid or gas release. The stream is a surface flowing pattern of liquid hazard material that is affected by gravity and topographical contours. The liquid release flows downslope whenever there is a gradient away from the point of release. A pool is a three-dimensional, including the depth, of a slow-flowing liquid dispersion. Liquid assumes the shape of the container and pool in a low area. As the liquid level rises above the confinement provided by the terrain, the substance flows outward from the point of release. If there is a significant gradient or confinement due to terrain, this flow forms a stream. The irregular or indiscriminate deposit of a hazard material is such that it is carried by contaminated responders or vehicles driving through it. In the event there is a release, facility and pre-incident surveys may contain plume dispersion models to help estimate the size of the endangered area. Computer software such as Cameo, Aloha, and HPAC can also assist in the prediction of plume dispersional patterns. First responders may consult the ERG for isolation and evacuation distances. With exposure and contact, a container risks dispersing its contents and the container itself on different types of exposures with people, the property, and the environment. In some cases, you can use the ERG to estimate the size of an endangered area. Some hazard materials may present a threat to one specific exposure type, such as marine pollutants that threaten fish and other marine plants and animals, and others present a threat to all types. When you evaluate the severity of exposures, consider the hazards present, the concentration of the material, and the duration of the contact. Consider the following exposures in hazardous and risk assessment. People, which includes responders and others in the path of hazardous materials. The environment, which includes the air, the water, the ground, and life forms other than humans, and the potential effect on the environment varies with the location in which the product is released, as well as its characteristics. The property, which includes things threatened directly by the hazardous material or the energy liberated at the time of release. Just remember that contacts are associated with the following general time frames. Immediate is milliseconds or seconds, such as an explosion or detonation. Short term is minutes to or hours, such as a gas or vapor cloud. Medium term is days, weeks, or months. That could be like with pesticides. And long term is years to generations and could be permanent from a radioactive source. With harm, harm is defined as injury or damage caused by exposure to a hazardous material. The three mechanisms of harm in a hazardous material incident are energy release, such as thermal, mechanical, chemical, pressure, electrical, or radiological. The second is corrosivity, and toxicity is the last. There is one review question for this section. How does General Hazardous Materials Behavior Model help predict hazards at hazmat incidents? Look on pages 211 and 212 of the manual for your answers.